Now, as we start the last chapter of what we'll be doing in Math 1103, this is sort of a lead-in to Math 1108 that most of you will be taking. But again, you want to earn at least a C in this course. This is the prerequisite for the Math 1108 or other courses. So we're going to do systems of linear equations. And here, what we're looking for is determine whether a given ordered pair is a solution to a specific system of linear equations, estimate the solution by graphing of a system of linear equations with one solution, and then I'll show you on a graphing calculator how to solve systems of linear equations. But we'll be doing some graphing, and as background for this, I want to just go over what we're doing here. Now, in an earlier chapter, we went over graphing in standard form or in slope-intercept form a graph by plotting points or by using other techniques. And let's say you get a line that looks like so. Now, this is positive slope. Now, suppose, as part of our scenario here, we get a second equation, whether it's in standard form or slope-intercept or whatever, and the graph looks like so. Now, notice that along each of these lines, there's an infinite number of points that is ordered pairs, but right here, the lines are intersecting. And what does that indicate? Well, it indicates that the ordered pair of one equation is a solution for that equation and also a solution for the other equation. So in this system of equations, this is what we're shooting for. Where would these lines, and we said again, this one is positive, as a little review, positive slope, and this one was negative slope. But that one unique point is a solution for both equations. And looking at this, what would it be? Well, if this were a negative 1 here, and this is about a positive 1, the ordered pair would be a negative 1 and a 1. Now, if we graph these systems of equations and find this point of intersection, we say we have solved these equations simultaneously. Now, another scenario for all of these would be you graph one line, and then you graph another line, and notice the lines are parallel. So would there ever be an intersection here? And the answer is no. So for this system of equations, there is no solution. So here there is one solution. Here there are no solutions. And then another scenario is you graph one of the lines, and then you graph the other line. Let's see if I can do this. And lo and behold, the other line is right on top of the first line. So what does this indicate? Well, that in fact, even though the equations didn't look like it initially, they are the same equation. So, since there is an infinite number of points along each line, and the solution for one is a solution for the other, for this scenario, there is an infinite number of solutions, and we're going to have a special way to write this. Now, this is something that's going to be a theme throughout this chapter. There are three possibilities: one solution, no solution, an infinite number of solutions. Now, the first one is to see if we can find that solution by graphing. But they also want us to do a little substitution here to see, when they give us a point, is it a solution for both equations? So with that in mind, we'll move on now. So we want to know, is this ordered pair a solution for this set of equations? So what we do is we substitute. The x is a 2 minus, now the y is a 1, so it's 2 times 1. Does that equal 0? We'll just do the substitution first. And now this is 3, and our x value is 2, and our y value is 1. Does that equal 7? Well, here this is 2 minus 2 equals 0, so that is true. And this is 6 plus 1 is 7 equals 7, so that is true. So again, they're just asking, is this the ordered pair? So if we were to graph these two lines, the place of their intersection would be at 2, 1. And they're going to show us this a little bit too, I'm assuming. So 2, 1 is a solution to those original equations that we had. Now here we're asked to show that this ordered pair is not a solution. So we're going to do the same thing. So our y is 4, and our x is 0. So a negative 0 plus 4, let's just do the substitution first. And this is 4, and this is 2 times 0 plus 1. So here, 4 and negative 0 is 0. So 4 equals 4. This part is true. But then 2 times 0 is 0. 4 does not equal 1. So this is not true. So this, by substitution, we have proved is not a solution. Now, in this next part, we're actually going to, and in MATLAB, plot the equations on a graph and then look to see the point of intersection if there is one. If the lines are parallel, there's not going to be any solution. Or if the lines are on top of each other, there's going to be an infinite number of solutions. And we'll look at some strategy for this. So, let's put this on a graph here. And once again, you want to determine, and I'm going to make a little graph for us to put our work on. Now here we're sketching. When you put it in MATLAB, it's quite formal. So I think for this, we could make a little X and Y intercept t-chart here. And this one is in slope-intercept, so we can plot it from that. So with that in mind, this is our x, y, a 0 there and a 0 there. So if x is 0, y is 6. And if y is 0, x is 6. So let's plot this one. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We have a dot there and a dot there. We're now going to do our line, and that's what this one looks like approximately. Okay, now this one, since it's in slope-intercept, we know our slope is 1, our y-intercept is 4. So we're going to go to 4 and put a dot there. Now the slope is 1 over 1, so we go over 1, up 1, and then over 1, up 1. So our second line is going to look like so. Now, the thing about graphing, especially when we're sketching it, you know, they're not really on the exact spot. So we're going to kind of guesstimate that that looks like the closest thing is a 1 and a 1, 2, 3, 4, 5. So I'm just going to assume that my ordered pair is 1, 5. Now, if I put these values then into my equation, 1 plus 5 is 6. Yeah, so this one checks. And if I put my 1 there, 1 plus 4 is 5, equals 5, and this checks. So again, it didn't quite match because this is just a sketch of a graph. So we're sort of estimating, and this is what we had to do in the old days when we were doing it on paper. Now, when you put this in MATLAB, you're going to get a nice intersection at this particular point. So let's look through this. And there it is. Makes a nice, proper graph. And if we had grid lines, that would help too. But even with grid lines, sometimes if we're penciling this in, it doesn't work that well. Okay. And we checked it, and it all works out here. Now, we're asked to solve this one by graphing. So again, what technique would you use here? And I'm just going to sketch it initially. Now for the first one, it's 3 over 1 is our slope, and our y-intercept is 0. So we put a dot there, and let's put some points here. 1, 2, 3, 4, 5. So this is going to go there at the origin, and then over 1 up 3. So right about there. And now I put my line in. And again, when you do this in MATLAB, you're going to get a nice, accurate thing. Now, this other one, we have to find first how to graph it. And for this one, I think I would convert this to slope-intercept. So y transpose the -3 becomes 3x here. And our y-intercept is a -4. Now, I don't know if you notice here, but now we see our slopes are actually the same, but our y-intercepts are different. So when I do that, and I go down here, 1, 2, 3, 4, and I go over 1 up 3, I actually get a line that should be, I'm off a little bit, but it's going to be parallel. See, this one is should be right over there. and the lines are parallel. And again, sketching is a little bit difficult, but you can see if we put them both in slope-intercept that our slopes are the same, but our y-intercepts are different. One of the techniques we said, that was what we indicated to be parallel lines. So let's see it done a little bit more accurately here. And there we go. When you're sketching it, that's why it was always a challenge. So you had to kind of perhaps look at some other thing to verify the points. There is no intersection. Now, a key word I want you to add to your notes is when there is no solution, we say the system is inconsistent. Now, if there is at least one solution, as we had in the previous item, then that is consistent. But if there's no solution, it is what we said, inconsistent. Okay. Now we want to solve these by graphing. So this one is already in slope-intercept form. So again, we're looking for strategies here. And I'm suggesting you take this second equation, which is 2y, bring over the x as a negative x, and then plus 6. So from standard form, I'm putting it into slope-intercept. Now I'm going to divide everything by 2. Remember, there's a 1 there, so put a 2 there. And then this is a 2. So now for this second equation up here, that was in standard form, we're now putting it in slope-intercept form. We get y equals a negative 1/2 x plus 3. And then what do you note? Well, these equations are the same. So that when we plot them, we'll plot the y-intercept, which is the same for both. The slopes are the same. The lines are on top of each other. So how do we put this into MATLAB? Well, we use set builder notation. Let me just write it out for you. So we put a brace. We say x comma y, our ordered pair, is such, that's that vertical line. And then we can write either of the equations because they're actually the same. X plus 2y equals 6. Okay, let's see what they show us here. So the lines, when we graph them, are actually on top of each other. So we say there is an infinite number of solutions. Now, since it has at least one, these equations are consistent. And are the equations the same? Yes. So we say the equations themselves are dependent. Well, you'll notice in the other two scenarios, the equations were different. So when the equations are different, we say the equations are independent. So a little more background. And there we go. Nice job. Okay, here they want us to solve the system of linear equations. This is in standard form. This is in standard form. So I would solve each of these, and we'll do it here, by putting them in slope-intercept. And there's this equation here. The blue line is the top one. The green line is the other. And then as we go to plot them, they're not on a grid line. So they're estimating it to be 2 and a negative 1/2. Well, then what do? Well, you put these values in there and see if they make the statement true. So when I looked at that, it didn't look like a negative 1/2. So this is not true. And that one's not true. So when you checked your estimate, it didn't satisfy the equation. That's why when graphing is a little bit challenging, because if it doesn't fall on a grid line, it's hard to read the solution. Now, the exact solution was this. So how could you ever figure this out? You could never pick these fractions out from a graph. So in the next section, we're going to show you how to solve these equations algebraically. And that way you don't have to worry about reading them from a graph. But the use of the graph to show you sort of what's happening to these equations. We're looking for that point of intersection, or no intersection, or infinite numbers of intersection. Now, we're going to use a graphing calculator to do these. And I think I'll put this in a separate section where we'll give you a little background on graphing. But right here, this is the examples. Again, to use this into a graphing calculator, you usually have to solve for y. So they have to be in slope-intercept. So let's wind this one up, and I'll make another little one on just graphing.